Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper trending on X, published on January 6th, 2026, just 2 days ago. It details the massive architectural shift required to turn passive large language models into autonomous, goal-driven agents that can perceive, reason, and act. The paper is titled "The Path Ahead for Agentic AI, Challenges and Opportunities." And as we'll see later, the proposed framework for bridging these capabilities offers a very clear roadmap for future development. To understand this evolution, Table 1 maps out 4 decades of progress in language modeling. It starts in the 1990s with statistical approaches, which established the basic idea of sequence prediction. As we move through the 2000s and 2010s, we see the rise of neural networks and transformers, represented by models like Word2Vec and BERT, which added crucial semantic context. Finally, the 2020s section highlights how modern scaled systems, such as GPT-4 and Llama, have developed the emergent reasoning and tool use capabilities that define agentic AI today. Next, Table 2 contrasts the fundamental shifts across 3 paradigms: classical symbolic AI, standard large language models, and modern agentic AI. In the core characteristics section, notice the progression of agency. It moves from reactive in symbolic systems to passive in standard models, and finally to goal-directed behavior in agents. The operation flow row highlights this best, showing how agents use a recursive loop of observe, reason, act, and reflect. However, the limitations row reminds us that this autonomy comes with stochastic, probabilistic outputs, unlike the predictable transparency of classical code. Alright, Table 3 contrasts the architecture of a single autonomous model with a full multi-agent orchestration. In the scope and coordination rows, we see that a single agent handles tasks end-to-end within a self-contained loop, while a multi-agent system decomposes complex goals across specialized roles, using negotiation to manage the workflow. This trade-off appears in the failure modes row. Single agents face single-point failures, whereas multi-agent teams must manage cascading coordination errors. Finally, the examples row grounds this, comparing basic React loops to team-based frameworks like AutoGen. So Figure 1 visualizes this cycle in practice, mapping out the core components of an agentic AI system. The process begins on the left, where the environment and perception modules capture raw observations. These inputs flow into the central large language model brain, which handles the heavy lifting of reasoning and planning. Crucially, notice the vertical link to the memory block below. This allows the system to maintain context over time. Finally, the action component on the right executes the decision, generating feedback that loops back to the start. While the previous diagram outlined the general components, Figure 2 makes this concrete by showing a single agent handling a financial query using the React architecture. It starts with the user query on the left, which feeds into the reason module where the large language model identifies any missing information. Next, the agent moves to the act phase, invoking external tools like a calculator to get the interest rate. Crucially, the reflect step evaluates the result against constraints, potentially looping back if more work is needed before delivering the final textual response. Okay, scaling up from the single agent we just saw, Figure 3 illustrates a multi-agent collaborative workflow. Instead of one model doing everything, the user query first hits a planner agent, which breaks the task into specific objectives. Then, specialized roles take over. A research agent retrieves sources and passes them to a writer agent to draft the content. Finally, a reviewer agent validates the output, and if it fails, that dashed feedback loop sends it back to the top for another try. Wrapping up, the big takeaway here is that transforming large language models into true agents requires more than just scaling up parameters. It demands a structural shift toward verifiable planning and hybrid architectures that ensure these systems remain safe and controllable in the real world. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.